much. So today I will be speaking about integrating renewable energy systems into buildings. So this is just a general introduction to integrating various types of renewable energy systems into a building project. I'll spend about a third of the time explaining different types of technologies that you may like to consider, and some general tips about what you should think about if you were to incorporate them into a buildings project. And then I'll spend the rest of the presentation going over a case study of a zero energy office building in which some of the strategies that I discussed previously will be included into that case study. To start out, just a quick reminder, I am with ASHRAE, as Maria introduced me, the president-elect of ASHRAE this year. ASHRAE is a global organization representing technical expertise in the buildings industry. Just a quick overview of ASHRAE on this slide, and later, if you'd like to review these slides, you can go back and learn a little bit more about ASHRAE. The question is why is it important to think about renewables in buildings? To give you some context, remember that buildings consume about 40% of the total energy consumed on this planet. That statistic, about 40% of the energy is used by buildings, is fairly consistent from country to country across the globe. Buildings do consume a very large portion of energy, and most of that energy, at least right now, comes from fossil fuels. The mix of that fossil fuels is changing, but it still comprises mostly of coal, natural gas, and fuel oils, but other petroleum products. And so when we're using that much fossil fuels, as we all know, there are environmental impacts from those fuels that we need to think about. How can we mitigate them? One solution to that is through using more renewable energy. Another thing to remember is that most of the buildings that are constructed have a fairly long lifetime. So the decisions that we make today are going to be decisions that will impact the amount of energy needed to operate those buildings for 25, 50, 75 years into the future. So it's important to think about what can we do now to minimize the amount of energy being consumed from fossil fuel resources as we are designing and operating our buildings now. Another thing to consider, final one here, is that thinking about the increase in how much energy we are continuing to use on this planet, we're expected to continue our worldwide energy consumption by about 1.4% per year in the coming years. That means, oops, we lost the screen. That means that buildings are going to be consuming, did it come back? Yes, it did, okay. About 86 trillion kilowatt hours of energy per year, which is a huge amount of energy. And if we can use some of that with renewables, meet some of that energy need with renewables, we are going to have a very large positive environmental impact about how our industry is contributing to the global climate conditions that we are seeing changing on this planet. So moving on to the topic of this presentation, what type of renewable energy resources make sense in a built environment? Well, it's just about any type of resource that's available at the site of the building. The ones I'm going to focus on in this presentation are those first four listed on this slide: solar, wind, geothermal, and biomass. I'll give just a brief summary of each of these before we go into the case study. Before deciding which type of renewable energy resource to consider, the very first step in all projects is to understand what resources are available at the site where the building is located. There are renewable energy resource maps that are easily accessible on the internet. In fact, today I typed in solar resource map Serbia and had no problem with the very first link to come up to be this map. Understanding based on these general resource maps is a place to start. Knowing if you have a resource in your area then can help you decide if it's worth your time to investigate further how to use that resource to offset energy loads in your built project. As I said, I'd start out with those four, describing a little bit of information about those four different types of renewable energy resources. The first one being solar. It's becoming very common. Two main ways that we use solar in the built environment, either with solar electric systems or solar thermal systems. Solar electric systems, most of them are grid connected, which means you have the photovoltaic array that's either on the building or near the building, that the power that is produced by that photovoltaic array is fed directly into the building to offset electricity loads in that building. Any loads that the PV system cannot meet are then met with the utility grid that's also tied to the building. If there happen to be excess electrons that are produced by the PV system that cannot be used by the buildings, those then go back into the grid to be used elsewhere. Solar thermal systems in buildings are typically used for supplying hot water, whether it be for domestic hot water needs, maybe light industrial needs if you have a hospital or a place with doing laundry or some other kind of medium temperature needs, or you could have more industrial hot water systems. And in this picture it's showing, I don't know why it keeps going back, it's showing a high temperature system next to a prison. So it's meeting all of the kitchen needs, the laundry needs, the shower needs, everything that's needed in that larger facility. When considering design considerations when doing a solar system, it's really important to have access to the sun, especially for solar electric systems. Any kind of shading on a solar electric system will drastically impact the amount of power that system is capable of producing. So having good exposure to sun is the #1 priority. Orientating and tilting your array to maximize the performance according to whatever types of loads you're trying to offset in the building is also an important design aspect. So doing analysis, there are tools that are easily accessible on the web to help to understand what kind of output you could get from a solar electric system depending on its orientation, its tilt, where it's located, and any kind of shading expectations that you have that might come across that array during a typical day. So understanding the performance of the system and how that's going to relate to the load profiles of the building is an important step during the design phase. Also understanding what kind of grid connection issues there might be for a solar electric system. Each utility has a different set of requirements for how it wants to have distributed generation systems tied into its grid. And so being familiar with what the utility is requiring in the area where your built project is located is something else that you need to do up front. Thinking about wind systems, same thing, start out by understanding if there is a resource in the area where your wind turbine is going to be installed. The next thing is to recognize that wind is really site-specific. You may have very good wind resource in the area, but at the exact location where you want to install your wind turbine, those wind conditions may be different. So measuring the actual wind resource that you have at the site where the turbine is going to be located is something you should plan to do for a wind system for a buildings project. So setting up a wind anemometer system, measuring the actual wind resource over a period of time. It's preferred that period of time is 12 months if possible. If there is not that much time available, then at least several months so that you get a good estimate about how much wind is actually there. If there's a good wind resource, then installing a wind system for a building does make sense. Wind energy is of the renewable electricity options is a very low-cost option. Wind turbines are also proven to be durable, and they survive many different types of conditions over a long period of time. It's a very mature and robust industry, so if you do have a good wind resource, it is a good system to choose. Geothermal systems. There are two ways to consider geothermal energy. One is direct. If you happen to be near a place where there is a heat source near where the building project is going to be taken, such as access to hot water coming from a geothermal resource in the ground, it can be used for space heating, for preheating domestic hot water, any kind of thermal load you need. The reality is those locations where direct geothermal resource is next to or very nearby where the building project is are very site-specific. There are a few places on the planet where it's easily accessible and a lot of places where it's not. So another form of access to the geothermal renewable energy resource is using geothermal heat pump systems, where you can take advantage of the constant temperature of the Earth's crust to help provide heating or cooling to a building. These systems make the most sense in climates where you do have both a heating load and a cooling load for the building, so that you can take advantage of that constant temperature of the Earth's crust all year round. And finally, to briefly talk about biomass systems. Biomass systems are taking advantage of that, energy that's stored in organic matter in different types of materials. So thinking about what that biomass resource could be, it could be agricultural waste products, either from crop products or from livestock products. It could be other plant products, such as forest thinnings for areas that are working to maintain the health of their forest, and so they thin those trees and bring them out. Can turn that waste lumber into pellets or just into large chips and feed them directly into a boiler to burn. It could also be municipal waste, and which personally I think that's a pretty funny renewable energy resource, but in many places around the world it is considered a renewable energy resource. We continue to produce waste. It goes into a landfill, and much of that landfill waste can be used in a couple of different ways, and so it's considered a renewable energy resource. How is it used in the buildings? Most of the time, biomass is used to provide thermal energy to the building. So it's burned in a boiler and used to create hot water for space heating or campus hot water district heating systems, or any kind of other thermal needs. But if you have a larger system, it can be burned in order to run a generator and create electricity for the building, if that proves to be a better use of using that available biomass. So to wrap up the introduction to renewables in buildings in general, here are some considerations for all renewable energy projects. I already mentioned how important it is that the resource is available. It's important that the resource is available near the building. The nice thing with solar energy is it's available right at the site of the building. If you are in a place with good wind, you'll have wind conditions at the building. If you're going to be using biomass, you'll have to bring it in from someplace else in most cases, unless you have a campus that's producing its own kind of biomass, its stream of biomass from processes or other activities going on the campus. So if you do plan on using a biomass system, make sure that you have the resource available within a range of the building site, so you can easily bring that biomass to the building. You have a place to store it at the building before it is being burned, and you can process it at that site. So it's just something to consider to think about in all these renewable systems, is not only do you have the resource available, how easy is it to get that resource to the building. Understanding the building's energy load profile. A lot of times you'll hear it's important to combine energy efficiency with renewable energy systems. The reason for that is if you can decrease the total energy load of the building, then you need less additional energy generation to offset those loads. And so a smaller renewable energy system can offset a larger portion of an energy efficient building's energy loads. So understanding what those load characteristics are, understanding when the loads occur, can you match the energy that you are providing to the building from renewable systems with the time that the load in the building is actually occurring. So these are the types of questions to think about when designing energy systems for buildings and planning to use renewables. There are incentives that are available in many parts of the world to help decrease the cost of renewable energy systems investments. There are also different types of financing mechanisms available to help pay for those systems. So understanding what those incentives and those financing mechanisms are up front may also help inform the design of the system itself. So there's a couple of other things that are listed on this slide, but it's just in general the types of things that you need to consider when you are beginning to design and invest in renewable energy systems for buildings. So moving on, I'd like to quickly talk through a case study of a building where renewables have been used to help make this a zero energy building. But as I mentioned before, matching renewables and energy efficiency design is often what is done in order to help buildings become low energy buildings. And in this case, having a very aggressive energy efficiency design is what really made it possible to make this a zero energy building. The name of this building is the Research Support Facility, or the RSF. It's located in the United States, in the very central part of the United States, where it's a sunny, dry climate. And you'll see how that climate has been used to help with the energy performance of this building. It's a large office building. It is designed to accommodate 1,300 people. I don't know why it keeps popping out, but we'll get it back. The building is designed to accommodate 1,300 people. It is about 33,000 square meters, constructed in two phases. The first two wings of that original slide I showed were the phase one. The back wing in the original slide is the phase two. Very aggressive energy efficiency loads were set at the beginning of this project. As you can see that it has a low required energy utilization index, or EUI, for an annual basis. Excuse me. I translated the 25 kBTU per square foot per year into, I hope this is the correct, that's a hard thing to translate into metric. But I believe it translates to about 79 kilowatt hours per meter squared for this building. This building is about 90% more efficient, at least in the United States, than the average office building that we find across the country. We have an annual survey, or I'm sorry, a survey that's completed every 3 years that looks at energy consumption in the various building sectors. The energy consumption for office buildings in the United States typically range at about 90 or so kBTU per square foot per year, or about almost 3 times as much as what the required EUI for this building is. This building from the beginning was required to be zero energy under all definitions of what a zero energy building was at the time. And it was required to be constructed in a firm fixed price scenario. So the price per square meter for this building is competitive to a Class A, that means a high quality office building that would be constructed in the region where this building is constructed. So this building does not cost any more than a typical office building in this area. And that was required by contract from the very beginning. So the requirements or the definition of what a zero energy building is can be found in this document. And that is a building where on a source energy basis, so that is looking at how much energy is needed in order to produce a kilowatt hour of energy at the utility. So on a source energy basis, that the actual annual delivered energy is less than or equal to the on-site renewable energy that is produced at that site of the building. So this is the official definition that in the United States our Department of Energy has produced, and ASHRAE also uses as its definition for a zero energy building. Oops, I went the wrong way. So how was that done? I'll go through some strategies that were incorporated into the design of this building. One is a very aggressive daylighting design strategy. The reason why this building has those narrow, long wings that you saw on the initial slide is because that's the maximum width that the building footprint can be to effectively bring in daylight across the entire width of that building. So as you can see in this picture here, this is one of the typical office wings in the building, that there is consistent daylighting from the outside walls. The long walls of the buildings are facing north and south. So there's the same amount of daylight at those exterior walls as you'll find in the interior space. One way they were able to bring that light into the space is by having very bright surfaces. That's why you see so many, the white walls, the white ceilings, the light-colored office furniture. But there's also some special designs to help bring that light into the space. The amount of glazing on both the north and the south-facing exterior walls of this building was calculated to bring in the quantity of light that was needed to keep the space lit. But you'll also notice in this slide here, if you notice the windows on the right, there are two parts to those windows, a lower part and an upper part. That upper part is very clear glass. It does not have any of the low E coatings or any other kind of barriers that would prevent light from coming in. So the maximum amount of light possible comes in through those upper windows. There are also louvers in those windows that direct the light up to the ceilings, and you can see bright spots on the ceilings. And what that is the light being directed from this upper portion of the windows onto the ceilings so it can bounce down into the center of the space. So this is a multi-dimensional daylighting design strategy that has gone into ensuring that these spaces are fully lit. And in fact, during the daylight hours, these spaces are 100% daylit. No additional light is needed in the building except for in some of the common areas where the conference rooms are located. Like the conference rooms, there's a fitness center, library, coffee shops, that sort of thing in the connecting common areas of this building that don't have the exterior walls where they can get access to daylight. Other than that, in all of these work areas, it's 100% daylit. So what does that mean? This is a chart showing the several things. The top bar is showing the baseline calculation. If this building complied with or was designed to meet what is required in ASHRAE standard 90.1, that's what the lighting density profile would look like. The middle line is showing what the expected profile would be in the models that were formed before the building was constructed. And then the colored lines on the bottom are showing the actual performance of the building on a typical day, typical bright sunny day when this daylighting system was in use. So what we're seeing here is that the daylighting system actually works very well, that the lights, electric lighting system does not need to turn on in most of the building. The other thing that was discovered, you can see how the green line goes extending off to the right side of the modeled lines. What this indicates is that people were staying in the building later into the evenings than was anticipated. People did not go home at the end of a typical workday, but instead stuck around, I guess, continued to work. So as a lesson learned, this is showing that it's important to be realistic about the occupancy schedules in the buildings when understanding the predicted loads for those buildings. But even with the lighting systems being on longer than anticipated, it's still much lower than what the base case or the original simulation models expected. So this is just a really simple graphic showing the human impact on energy performance in buildings. The yellow section is humans impact lighting as a significant portion of the buildings, but the green part is where people, us in buildings, really have our impacts in the building's energy systems, and that's on the plug loads. And so in addition to the daylighting design for this building, the plug load design was seriously considered, and steps were taken in every aspect of where there were plug loads in the building in order to reduce those loads. And in fact, after the plug load reduction strategies were put in place, nearly 50% savings was achieved in those plug loads. So that included things like having designing the building so that it has very bright and easy to use stairwells. So people then are more apt to take the stairs instead of taking the elevator, because they're easy, it's a pleasant place to be, other people will be using the staircases, so it's a place to interact with coworkers and others in the building throughout the day, and it impacted the behavior of the occupants, so they were not using the elevators, which typically are a very large plug load for the building. Other measures that were taken include the layout of each of the office workspaces. And so the types of computers, at the time this building was constructed, back in 2010, there were still a fair amount of desktop computers. So policy went into place that said, there will not be any desktop computers in this building because the laptop computers are so much more energy efficient. So before moving into the building, anybody who did not already have a laptop, their computer was replaced, so then they could have the laptops. There was also some policies put in place saying which monitors could be purchased for people's use at their desk to ensure that only the low energy monitors were installed. The telephone systems in the building. 1,300 people, which means you have 1,300 phones, plus the phones in all the conference rooms and the other public or common use areas. It's a lot of phones. That's 1,500 phones about in the building. And so using using very low energy phones, the 2 kilowatt phones versus the ones that typically cost or use about 30 kilowatts per unit, were installed throughout the building. So all of these measures help to add up to reducing those plug loads by 42%, somewhere around 50%. I'm sorry, I didn't notice that it just changed again. But you'll notice here this light green bar in the middle, this bar here, that represents the data center in the building. So there is a large data center that serves not only this building, but also the campus that this building is on. So the data center is a plug load. It is part of what you need to run the building, to do the business in the space. It's a lot of computer equipment in one small space. And as you all know, data centers use a large amount of energy unless they are designed with efficiency in mind. There's been huge advances in data center design strategies over the last 6-8 years. At the time this building was constructed, this was one of the most efficient data centers in the world, with a PUE of about 1.35. Now that PUE is nothing to be proud of anymore because it's not, there are data centers that are a lot better, but at the time this was very advanced. And how did they do that? They were doing hot aisle containment, reusing data center waste heat, using a variety of strategies for cooling that space. These were all very innovative at the time and helped to reduce the plug loads for the building. A chart showing the base case plug load profile, that's the dotted line, and the actual base plug load loads that were measured over several months, and you can see that the plug loads in this building are much less than what the base case system anticipated they could have been. The building envelope was also considered as to look at efficiency measures. A lot of thermal mass is used in that building, with the thermal mass on the interior side of the building so that it can store the heat or it can stay cool at for longer periods of time. There's night purging that occurs with natural ventilation to help cool that mass during the night in the summertime, so it can delay until later time of the day when the cooling systems need to turn on. The HVAC system includes a dedicated outdoor air system for providing ventilation air, but all heating and cooling needs beyond what can be met with the natural ventilation system is met through a radiant system. So there is a campus hot water and chilled water system that provides the hot and chilled water to the radiant system in this building. A wood chip or a biomass system is used to help offset approximately 50% of that thermal load for the building, and very high efficiency water-cooled chillers are then used to provide the chilled water for the building. And I didn't know how to convert this to metric, but what this means is the amount of cooling provided per square meter of this building is about 1/3 of what you'd find in a typical office building in the United States. We already talked a little bit about the natural ventilation system. There are both automatic or automatically operable windows as well as manually operated windows. The windows that are operated with the automatic control system, it is a portion of the total portion of the windows that are controlled by that system is what's needed in order to ensure the type of natural ventilation impacts that's desired by the building design. As a picture installing the radiant heating system, it's all in the ceilings of the building, so it's providing heat and cool from the top down to the floor. The reason for that is because of the dedicated outdoor air system is providing ventilation air through the plenums and a raised floor system. So you have to do the heating and cooling from above because the ventilation is coming from below. Finally, there's a solar ventilation preheat system on the exterior of the building. This is the south wing of the building. The dark section in this photo shows that solar ventilation preheat system. What it does is it heats the surface of that wall. A thin boundary layer of air is heated and then drawn in through perforations through that surface. Then that's brought into the building to help offset the heating ventilation loads during the winter months. So looking at the mechanical system performance of the building, the dotted line again is the base case, and the colored lines are showing the performance over several months. The red line that's on top is the first month that this building, that the HVAC system performance was being measured. As you can see, it's above what was expected. That means that there were some issues going on in the system. Because they measured the performance of this building, they recognized there were some issues. They went into the systems and found where control settings weren't quite right. Maybe there were some dampers or valves that weren't operating as they should be. Those things were fixed, and after 1 month, you can see after that, the performance of the building performed at or below its expected performance. This chart is showing the month-by-month comparison of the model performance versus the actual performance during the first year that data was collected for this building. In general, the lines are pretty close, but what's really important is the red and blue line through the middle, which is measuring the cumulative energy utilization index for this building. The modeled and the actual EUI for this building is right on target, as you can see throughout that entire first year. The second phase was constructed within about a year from the first phase. Because it happened so quickly, lessons learned from the first phase could be incorporated into the design of the second. As a result, the second phase performs more efficiently and it costs less to construct than it did in the first phase. So being able to incorporate those lessons learned right away was an exciting opportunity for this building. A list of some of the things that were used in that second phase to make the lessons learned that were incorporated. I'll let you look at that later. An important thing about a zero energy building is that there is somebody who is responsible for ensuring that building is operated and is performing at its expected levels so that it can continue to be a zero energy building. As we all know, over time buildings start using more energy here, more energy there, and pretty soon it's no longer an efficient building. A simple dashboard such as this is really helpful. This is the one that's used in this particular building. It is, where can I get the? It is an analog system that if the dial is in the green, things are doing fine. If it's in the red, you better go look and figure out what's going on. And these analog dials are shown for various systems throughout the building to help pinpoint where problems may be occurring so they can be fixed right away. So in the end, this is a photo looking at the campus. The campus extends all the way into the back of this photo. The buildings you can see in the middle upper part are still part of the campus. This single building increased the footprint of this building's of this campus's building space by 50%, but only increased the campus energy consumption by 10%. So a very low energy building helped to provide a lot more office space without having a large impact on the total campus energy consumption. Photovoltaic systems are used to offset the energy loads of this building. There are 3 main sites where this system is located. One is on top of the building itself. As you can see, there's about 850 kilowatts installed on the roof of the building itself, about 500 some kilowatts on a small parking area in front of the building, and then this large building in front is a parking garage that serves the entire campus, and that holds the rest of the system of just under 1.2 megawatts. Because the 2 parking areas were needed to place the array that's serving the zero energy building, the energy needed to run those 2 parking areas had to be included in the total energy calculations for the building. So the energy utilization index that was indicated includes what's needed to run the lighting systems in these 2 parking areas as well. So compared to other energy efficient buildings, where does this cost? The blue lines are showing the cost of this particular building sliced and diced in several different ways. Even if you look at the middle part of these lines, you can see that this zero energy building is right there in the middle of a range of very efficient buildings that are being monitored around the world. And so it does not need to cost any more to run a zero energy building as a typical building. So with that, I'm going to wrap up my presentation. Thank you very much. Here's my contact information if you have questions about this particular project or anything else that I've spoken about today. So thank you very much.
Thank you very much.